Soils are either cohesive or cohesionless. In this lab, we studied the shear strength of sand, which is a cohesionless soil, meaning the grains don't adhere to each other. The resistance of the soil to shearing is therefore primarily due to the interparticle friction, dependent on contact forces. The volume changes in the soil while shearing also play an effect. On the sand grain scale, the individual grains can move and roll around each other, increasing or decreasing the contact area between them as shearing occurs. The shear strength of sand is tested here in the Direct Shear Device, which models conditions along a shear surface. The shear surface is a horizontal plane across the middle of the shear box, which comes apart into two pieces. The soil is contained in the shear box, which is closed and screwed tight. A constant vertical force P is then applied. A motor-driven bolt then causes a relative horizontal displacement L as the soil is sheared. As the test proceeds, the displacement is measured along with the applied shear force T and the change in specimen height H measured by the top cap displacement. The shear resistance is then given by a simple proportional rule. The shear force is the product of the normal force and the tangent of the angle of shear resistance. These forces can be converted to stresses via division of the shear surface area. To complete a direct shear test, in addition to the box, you need to groove bottom and top plates, the top cap for load transfer, a funnel, a rod for compaction, the sand you'll be testing, and weights for the vertical load. You'll also need a scale to take measurements with. Before you start with the direct shear device, measure the total amount of sand in the container you have and record the total mass. With the box screwed together, measure the area of the cross-section using calipers. Then take multiple measurements of the box height from the bottom plate to the top of the box. Take an average of these measurements. To prepare a loose soil sample, use a funnel to gently pour sand into the shear box, keeping about a centimeter's distance from the end of the funnel to the surface of the sand when possible. When you are finished, gently smooth the top surface out without pressing hard on the soil to avoid compressing it. To prepare a dense sample, pour sand into the box into a thin layer. Then use a rod or block to tamp down on the soil, repeating this process over and over again until the box is nearly full. Regardless of what type of sample preparation was completed, the soil surface should be flat. Measure the distance at the top of the box with calipers and record the height of the sample using the difference of your box height and this value. Then, gently place the top plate onto the sample. The grooved lines should be perpendicular to the direction of shear. Now, record the mass of the soil remaining in the container you poured it from. The difference of these two masses is what is in the shear box. Knowing the mass, volume, and specific gravity of solids of the soil, you can calculate the initial void ratio and density. The top cap and hanger are then placed on the shear box so that the vertical load can be applied. The shear resistance of the soil is proportional to the normal load applied to it. As engineers, we are often interested in stress-based behavior rather than force-based behavior. The top cap disperses the point load across the sample. Common normal stresses applied for direct shear testing are 50, 100, and 150 kilopascals. With a normal stress selected, a mass of weights can be solved to be applied to the sample. Don't forget that the hanger has a non-negligible weight too. Weights are added to the bottom of the hanger. Be careful to lift them properly when loading the sample. Remove the two pin screws which keep the sample together. This step is vital. If you don't do this, you will simply measure the shear strength of the pins as they bend and make the box hard to get apart again. Turn on the recording software and see that all the readings are properly zeroed out. Switch the machine's motor to manual drive. This will look different depending on the direct shear device you are using. Now, use the motor drive and the digital readout to establish contact between the shear box and the load cell recording the shear force. Crank the wheel until the readout registers a very slight force on the load cell, meaning contact has been made. Keeping the value small but non-zero to ensure connection is maintained, switch the motor drive back into automatic. There are two strain gauges on the device. Affix the vertical strain gauge to the center of the hanger and have it depressed about halfway to measure specimen height increase or decrease. The horizontal strain gauge is located on the back by the load cell. This strain gauge only has to have a slight connection, as the direct shear device can only travel one way and compress the strain gauge. The remaining screws that didn't hold the box together can now be retracted. The frames are separated by their turns. Turn the screws 1.5 times for loose soil samples, or half of a single turn for dense soil samples. Locate the switch for the automatic motor drive. Now, turn on the software first and then the automatic motor drive second. The device will begin shearing the soil inside the box. Watch the behavior on the digital readout of the soil. Let the sample go for 6 mm of horizontal travel, or until both the shear force and vertical displacement readouts are steady and no longer changing. The loading behavior of the soil will be different depending on its initial density. Densely prepared samples will exhibit a peak strength and then collapse to a lower strength representative of the constant volume condition. Loosely prepared samples will show a simple increase of load and reach the same constant volume strength. The volume behavior in the direct shear test is represented by a change in height of the sample. Dense samples will initially undergo a brief compaction, but then increase in volume as the grains roll over each other and dilate before the volume becomes constant. Loose samples compress at a gradually decreasing rate until their volume becomes constant. The shear strength is measured by the cohesionless Mohr-Coulomb failure criterion. Pairs of normal stress and shear strength are plotted against each other. For dense tests, the peak strength results are used to form a peak strength envelope which has a higher strength than the constant volume condition. Loose tests and dense tests at larger displacements are both used to determine the constant volume strength of the soil. The slopes of these lines are the tangents of their respective angles of shear resistance.